Hello, this is week 8 of AP Physics, and in this week we're going to go ahead and continue Newton's third law and applications of that law. We're also going to use Newton's second law, force equals mass times acceleration. Let's go ahead and get to work. For our agenda, applications of Newton's third law. And lesson objective, students will be able to solve problems using Newton's third law plus Newton's second law, force equals mass times acceleration. We're going to go ahead and jump straight to the examples, and in this problem, example 4, they asked the combined weight of the crate and the dolly is 3 times 10 to the 2 newtons, or 300 newtons. If the man pulls on the rope with a constant force of 20 newtons, what is the acceleration on the system, which is the system's the crate plus the dolly, and how far will it move in 2 seconds? Assume that the distance, that the system starts from rest and there is no friction. So we'll be ignoring friction for this problem, and let's go ahead and get started. I'm going to start with a free body diagram just so we can get a good concept of what we have here. And so that's going to be a dot representing our crate, and there's 3 forces acting on this one. There's going to be force of gravity, Fg, and opposite force of gravity is going to be force normal, which has the same length, so because they have the same magnitude, just different direction. And there's the man pulling on the box, we're going to call that force pull. Alright, now values given from us says the combined weight of the crate and the dolly is 300 newtons. So that'll be 300 newtons in the negative direction. And the man is pulling the crate with a force of 20 newtons. So our force pull is 20 newtons. So those are the values that we have, and they want to know again 2 things. What is the acceleration of the system, and how far will it travel in 2 seconds? Alright, so we're going to get to the acceleration first, and then the displacement after 2 seconds. What is that displacement on the x-axis? Okay, so those are the 2 questions we're trying to solve for, and formula we're going to use. The first formula we're going to go ahead and use is for this one, force. Alright, so we needed to get the acceleration. The net force on here, force normal and force gravity cancel each other out, so the net force is just from the force pull. So that'll be our force net. That's our, which is mass times acceleration. Alright, so we have the force, which is 20 newtons. That's going to give us acceleration. All we need is the mass of the system. Okay, so we're going to use the force gravity to solve for that. Force gravity, that's just mass times gravity. Okay, so we know gravity is 9.8 meters per second square. We're just going to use 10.0 just to keep the math simple. And that's going to give us the mass. Once we have it, I'm going to substitute it here to get the acceleration of the system on the x-axis. Our force gravity was 300 newtons. Mass and acceleration due to Earth's gravity is 10 meters per second squared. I put negative because it is being accelerated towards the center of the planet. Alright, so we're just going to go ahead and divide by 10 on both sides. And that gives us our mass of 300 divided by 10. That's just 30 kilograms. That is the mass of the system, which is the crate plus the dolly. Next, we're going to go ahead and plug that in here. And the net force is the 20 newtons. And the mass is 30 kilograms, and that's going to give us our acceleration, which is, that's what we're solving for. I'm going to divide both sides by 30. So that's going to give us our acceleration in meters per second squared. 20 divided by 30 is going to go ahead and give us 0.667. So that will be our first answer. What is the acceleration? Alright, the next question that's asked of us is, can you go ahead and figure out what is the displacement on the x-axis after 2 seconds have elapsed? So the 2 seconds are given to us. Here they are on the problem. Alright, so we're going to go ahead and figure out the acceleration. We have the acceleration, the displacement on the x-axis. So we're going to go ahead and use this formula back from the first unit. Velocity initial times time, that's on the x-axis, plus acceleration, 1/2 acceleration on the x-axis times time squared. Okay, now initial velocity, they did tell us that assume that the system starts from rest. So therefore velocity initial is 0, so we can go ahead and ignore this part since we started from rest. So I'm going to simplify it a little bit. So it's really 1/2 the acceleration on the x-axis times time squared. Alright, so now let's plug in the values. 1/2 the acceleration was 0.667. Time was 2 seconds, and time is squared. Okay, so we're going to go ahead and get a calculator. So for this, so 2 squared is 4, 4 times 1/2 is just 2, so it's just 0.667 times 2, really 1.33. We're going to that's our answer. So the man pulling on the crate, after 2 seconds, he's traveled 1.33 meters, and his acceleration is 0.667 meters per second squared. Okay, that goes ahead and takes care of example 4. We're going to go ahead and move on to the next one, this practice problem 12. And in this one they ask you, what effect does doubling the weight have on the acceleration and also on the displacement? Alright, so let's go ahead and take a look at that. What if we doubled the weight? So the weight was 300 newtons. What if we were to double that? So now it would be 600 newtons. Okay, so let's plug in that 600 right there. So that makes this 60 kilograms. Alright, so the mass stays the same. So if we double the weight, now it has doubled the mass. Okay, now we plug that in here. Or 60 kilograms instead of the 30. What does that do to acceleration? It's going to cut it in half. Excuse me. So it's going to be 20 divided by 60. It is going to be 0.333. So rather than being 0.667, it's going to be half as much. So if we double the weight, it's going to have half the acceleration. What about the displacement that they traveled? Well, let's switch the acceleration. So that's going to be, let's see, 4 times 0.333 times 0.5. That's going to be 0.667, which is half as much. Okay, so the acceleration is cut in half and the displacement is also cut in half. Alright, so that would be the effect that doubling the mass would have on the crate. Alright, let's go ahead and move along to our next problem. This one's number 13. In this problem they ask you as the following question. A man pulls a 50 kilogram box horizontally from rest while exerting a constant horizontal force, displacing the box by 3 meters in 2 seconds. Find the force the man exerts on the box. And they ask you again, ignore friction. In this unit, in unit 2, friction will come in later after we're done working with Newton's third law. We're going to add to it later. Alright, so for right now we're going to ignore the friction and we're going to start with a free body diagram to get a pretty good understanding of what exactly is given to us and what they want from us. Alright, so the mass of the box is 50 kilograms. So now I can go ahead and get my force due to gravity, because you know that that is mass times gravity. So force due to gravity is 50 kilograms and 10 meters per second squared. So force due to gravity is 500 newtons. So I'm going to label that negative because it is in the downward direction. So negative 500 newtons. And this person, the man, is exerting a constant horizontal force. So I'm going to put force pull. There's also force normal, but we don't need it for this problem. It will be the same value as force gravity. It would be positive 500. Okay, now they want you to find the force. All right, force that's being pulled on it. Okay, so the force is going to be mass times acceleration. Okay, now the net force is just the force pull, because force gravity and force normal cancel each other out. So force pull is the same as the net force, since it's the only force that does not get canceled out. So we need the mass, which we have it, 50 kilograms, and we need the acceleration. Alright, so to get the acceleration, let's see, we've got the displacement and the time. So we're going to go ahead and use the formula we used earlier. Displacement is equal to velocity initial on the x-axis times time plus 1/2 acceleration on the x-axis times time squared. Alright, and let me see, does it say it? It does not say find the force. No, it does not say if we start from rest, but we're going to go ahead and assume that we're starting from rest. So I'm going to cancel this out. Okay, so now we have our displacement is equal to 1/2 acceleration times time squared. Now I'm looking for the acceleration, so I'm going to simplify it, get rid of the half, get rid of the t. So I'm going to multiply both sides by 2. That gets rid of the half, and now I'm going to go ahead and divide by time squared on both sides. So that gives us our acceleration on the x-axis. Okay, now what are we going to do with that? We're going to substitute it right here, and that's going to give us, so this formula I'm going to substitute it right here, multiply times the mass, and once we do so, that's going to give us the force pull. So our formula will look like this: mass multiplied times the acceleration, which was 2 delta t over time squared. Alright, so that's going to go ahead and give us the force pull, which is also the force net in this problem. Okay, so once we substitute all the values in, then we'll have our answer. So the mass was 50 kilograms. 2 multiplied times the displacement, they traveled 3 meters. Divided by time, it took them 2 seconds to travel that. 2 seconds, and that is squared. Alright, for this problem, I would definitely want to go ahead and take it piece by piece. So for example, 2 squared, that's a 4, and 2 times 3, that's 6. 6 divided by 4, that goes ahead and gives me 1.5. So 1.5 times 5 times 50, that gives me force pull of 75 newtons. Okay, so that goes ahead and gives us the answer to this problem. Alright, let's go ahead and keep on moving along. We're done with this problem, 75 newtons, so that's a force. Here we combine this formula with that one to get this, and plug in all the values. Sometimes in the AP test, they ask you, can you just figure out the formula? They don't really even want the value, like the 75, they won't ask you to solve for it. Sometimes they do, a lot of times they don't. Just tell us what formula would you use to solve for this. So then that would be the answer. M times 2 times delta, this delta x over time squared. So that would be your answer. Alright, let's go ahead and keep on moving along. Up next is problem number 14. And in this problem they tell you guys the following. It says a person is pushing 2 boxes across a frictionless surface. Assume that the mass of M2 is greater than the mass of M1. So therefore our first box is bigger than the second box. And that the boxes begin from rest. Draw a free body diagram showing the forces exerted on each box and write a formula for the system. Okay, so our first one is going to be free body diagram for each box. Okay, so the first box, remember that it's larger than the second box. So, this will be our first box. So because it's larger, therefore it's heavier, it has bigger mass. So I'm going to draw a pretty long vector for force gravity. There's also force normal acting on it. Okay. Also in this system, we got, for the first box, we have a man pushing on this box. So I'm going to put force push, so FP. But right here where there's contact between the 2 boxes, because there's contact, one box is exerting force on the other box and vice versa. So therefore I'm going to put force from box 2 going the other direction with the same magnitude. Okay, and next, that takes care of the first one. Let's go ahead and do the second one. Okay, on the second one it was a lighter box, so you'll see my arrow for force of gravity to be smaller because it's a lighter box, so therefore we have a smaller magnitude. Matching arrow for the force normal acting on it. Okay, and there's only one force acting on the box, and it's towards the right. I'm talking about the box in the front. that is force from box number 1, who's pushing on box number 2, which is the one on the right. Okay, so that would be the free body diagram for each one of them. Okay, now if you want the next question is just write a formula for the system. So that includes both of them together. Alright, how will we do that? Well, it will be force equals mass times acceleration. But for the mass, what do we put? We got 2 boxes in the system, so therefore it will be force, push, because that'll be the net force. These two cancel each other out, they're the same. And equals mass of box 1 plus mass of box 2 times acceleration. So that will be your answer for a formula for both of them, for the whole system. Alright, so that goes ahead and takes care of problem number 14. Okay, up next for us, we're going to go ahead and move on to an example. And this example, there we go. This example, example 5, has various parts. I have part A, B, C. So we're going to go ahead and get to it. It discusses a car that is on a slope. And we're going to go ahead and solve this one. So it says a car of mass M is on an icy driveway. Ice again because they don't want you to deal with friction. Okay, it says the incline at an angle is 20 degrees. Determine the acceleration of the car assuming the incline is frictionless. Alright, so that'll be part A. What would be the acceleration of the car? Okay, we have mass M and the angle is theta, is 20 degrees. So I'm going to go ahead and write that down. Theta equals 20 degrees. Alright, so let's start with a free body diagram. In this free body diagram, there's the hill. Here's the vehicle. And perhaps a little too high. Let me go ahead and bring it down slightly so I can get my vectors. A little bit better spot. So this is our free body diagram. There's our hill. Alright, and okay, forces acting on this. Let's start with force of gravity. So I'm going to draw an arrow going down, but in which direction? Straight down or perpendicular to the hill? The answer is gravity always goes straight down, always. So there's my FG, force of gravity. Okay, what other forces are acting on this one? Well, there's also force normal, and force normal is going to be perpendicular to the hill. So I'm going to move my free body diagram right there. And the length of it, I'll double check that I got it right. Looks about right. That'll be my force normal there. Okay, now I want to go ahead and break down my force gravity into its components. Now when you do so, remember force gravity is a straight down, always straight down. And on top of that, force gravity is going to be the hypotenuse of a right triangle we're going to go ahead and draw. So when we break it down into the x and y components, force gravity is always the hypotenuse on a right triangle. So the first part is going to be here. So this is my first component. And goes straight down. It is a straight line from force normal. It is perpendicular to the hill. Okay. And the next component is going to be right there. And that makes it a right triangle. Okay, what do you call this one? We're going to call that force gravity on the y-axis. I'm going to call this one here at the bottom is going to be force gravity on the x-axis. Now, force of gravity on the y-axis and force normal are matching forces, so they're going to cancel each other out. So what's the only force left over here? It is really force of gravity on the x-axis. Okay, so that's the only one left over. That's the only force that's going to be accelerating this car, which they asked us to go ahead and solve for the acceleration. Alright, so there's our free body diagram. The angle, by the way, is right there, is 20. It always matches the angle of the hill. Those two match, so that's 20. Yes, the hill is 20 degrees. Alright, so let's go ahead and figure out what is the value of force gravity x. Notice how the angle is here. Force gravity on the x-axis is opposite, and force gravity is the hypotenuse. So what do you use? Well, you're going to use sine. So it's going to look like this. Sine of 20 degrees is equal to opposite force gravity on the x-axis, over the hypotenuse, force gravity. Alright, now I want to solve for what is force gravity on the x-axis. That's the one I'm interested in. So I want to isolate it. That means get rid of force gravity. Force gravity. So they cancel each other out. And there we go. Force gravity is, force gravity on the x-axis is force gravity multiplied times sine of 20 degrees. Alright, next, do we have the value for what is force gravity? We actually do not. But what we do know about it is that force gravity is mass times g, m times g. So I'm going to go ahead and substitute those because they wanted us to use m for the mass. So I put m times g times sine of 20 degrees is equal to force gravity on the x-axis. Alright, so what is our acceleration? The acceleration for this vehicle is going to go ahead and be force equals mass times acceleration, right? That's the formula. Force equals mass times acceleration. The net force. Sorry, it says net right there. So the net force. I remember force normal got cancelled out because force gravity on the x-axis. On the y-axis, sorry. Force gravity, we broke it into its components. So that's the net force, force gravity. Alright, so we know what that is. That will go right there. Mass, we have it on the other side, so it will look like this. I'm going to get that substituted where the force net is. So it'll look like this. More mass times gravity times sine of 20 degrees is equal to mass times acceleration. Again, that and that, I just put this formula there. That's what I've done. Let's go ahead and simplify it. They wanted us to solve for A. So I'm going to go ahead and simplify. I want the A all by itself, get rid of the M. So to do so, I'm going to divide by M. That's gone, that's gone. So really the acceleration of the vehicle is going to be gravity times sine of 20 degrees. And that will be the answer for A. The mass of the vehicle is irrelevant. And sometimes students believe that they need it and they'll get stuck in the problems because they'll say, I can't solve it. They never gave you the mass of the vehicle. And if you notice, it cancels out. So the acceleration of the vehicle is just gravity multiplied times the sine of the angle of the incline of the hill. That's all you need. So that takes care of part A. Alright, I'm gonna write it over here. I have a feeling you might need it again. G times sine of 20 degrees. That will be our answer for part A. Alright, now let's go ahead and take a look at part B. In this problem it says, if the length of the driveway is 25 meters and the car starts from rest at the top, how long does the car take to travel to the bottom? Alright, so in part B, they give us the displacement, 25 meters, and they're asking us, well, how much time would it take to get to the bottom? Alright, the acceleration of the vehicle is here. We know that, here's the formula, G is 10 meters per second, sine is 20, so sine of 20 times 10 gives us 3.42 meters per second squared. That will be the acceleration. So we have the acceleration of the vehicle from part A of this problem. Let me label that. And now we want to know how much time would it take to reach the bottom if the driveway is 25 meters long. Alright, so let's go ahead and use this formula. Okay, so there's our displacement 25 meters, but I wanted to start here. The car is described as starting from rest, so therefore it's not moving. Okay, so now I can say, well, velocity initial is 0. 0 times time is just 0. So I'm going to simplify the formula. Okay, next. I'm going to go ahead and multiply by 2 on both sides so I can get rid of the half. My goal is to isolate the t. Okay, so I'm going to end up with this. Next, I'm going to divide by the acceleration. It goes right here. And so that goes away. I'm just going to erase it. And finally, I just want t, not t squared. So to get rid of that, I want to square root it. So I end up with that. So 2 times delta x over acceleration on the x-axis square root equals time. That's how long it's going to take to go from rest to the bottom of the driveway. Alright, so the actual math, 2 times the displacement, which is 25 meters, over the acceleration, which is 3.42 meters per second squared, and all of that will be squared. So you get your calculator, and let's plug it in. 2 times 25 is 50 divided by 3.42, and then you square root the answer. It gives us 3.82 seconds. That would be part B. That is how long this vehicle would take to get from rest to the end of the driveway, which is 25 meters away, about almost 4 seconds. All right, let's go ahead and move on to part C. What is the car's speed at the bottom? All right, so for that question, we already have, let's see, we have the acceleration, we have the time, and I'm going to go ahead and do my best to squeeze that in here. Maybe not. I'll erase how I got the formula. Part C, what is the velocity of the vehicle at the bottom? Just going to go ahead and use this formula from, again, Unit 1. And velocity initial 0, so its reality is just acceleration multiplied times time. Okay, and that's going to give us a velocity at the bottom of the hill, of the driveway, I should say. The acceleration was 3.42 meters per second squared. The time was 3.82 seconds. Multiply them together, and that's going to go ahead and give us a velocity at the bottom of the hill. And it's traveling at 13.1 meters per second. That is the velocity of the vehicle at the bottom of the hill. Alright, now, next section, this just for fun. What if they would have asked you part C without breaking it down to part A, part B, and part C, and just give us the formula. Again, sometimes they just ask you for the formula. So you know this is the formula for part C. Okay, so I'm going to put it here. And how do we get A? Oh, this was the formula for A right here. So I'm going to substitute that in. G times sine 20. Let me put, instead of the 20, let me just put theta so it can be any angle. And the time, well, I erased the formula, but it was this, 2 times displacement or the acceleration. And it was all square rooted. In the parentheses, I'll just put that. So that would be your formula. That's how we got time there, that's how we got acceleration there. And that would be the formula they ask you, hey, can you give us a formula for the velocity at the end? Alright, there you go. That would be it. It's just combining that formula with that one, putting them together. There's your answer. Alright, let's go ahead and move forward to next problem. And problem 15 is up next, and it's going to go ahead and piggyback on this problem. It says 15, if the car is parked at a more gentle slope, at a lower angle, what will the time required for it to slide to the bottom of the hill, how will it be affected? And explain your answer. Alright, so we're decreasing the angle because it's a more gentle slope. So let's go ahead and take a look at the acceleration. If we were to decrease this value, what would happen to the acceleration? Well, that will decrease as well. And if we decrease the acceleration, well, that's going to mean, because here the acceleration is the denominator, that's going to make more time. See the inverse, because the acceleration is the denominator, that would mean it will be more time. So smaller acceleration means it will require more time for the car to reach the end of the driveway. Alright, let's go ahead and move on. Now, problem 16. In this problem, they ask us the following question. Suppose a hockey puck slides down a frictionless ramp with an acceleration of 5 meters per second. Alright, so that's what's given to us. We have a hockey puck going down a ramp. We have an acceleration for it, 5 meters per second. So I'm going to write that down. Squared. Alright, what angle does the ramp make with respect to the horizontal? Alright, so the formula from the previous problem was acceleration was gravity times sine of, I'm going to just put theta. Alright, so now that's what they're asking us for. Okay, so how will we do part A? I want to isolate the theta. So I'm going to go ahead and divide by g on both sides. So what happens with the g here? It goes away. So since it goes away, it cancels out. I'm going to go ahead and erase it. Next, what do I do to get rid of sine? Well, you do inverse sine. So we're going to do it to both sides, so it'll look like this. Inverse sine of A over G is equal to the theta. And that's how you would solve this problem. Okay, so let's go ahead and plug in the values. I'm going to rewrite it a little bit. Theta is equal to inverse sine of accelerations, which is 5 meters per second squared, over 10 meters per second squared for G for the gravity. Okay, so now the inverse sine of 0.5, 5 divided by 10 is 0.5, and inverse sine of 0.5 will give you 30 degrees. Alright, so that will take care of part A in problem number 16. Let's go ahead and move on to part B. In part B it says, if the ramp has a length of 6 meters, how long does it take the puck to reach the bottom? Alright, so we have the acceleration and we have the displacement. It's going to go 6 meters, and they want to know time. How much time would it take? By the way, let me just write it, just because we did solve it. The angle is 30 degrees though. I don't think we'll need it for part B. So again, they want to know how much time would it take to reach the bottom. Okay, so it's a 6 meter ramp. So we're going to go ahead and go back to this formula. Plus 1/2 acceleration times time squared. Alright, so they want to know again the time. So just like the previous problem, we're going to go ahead and be solving for that. We're going to say that the puck starts from rest. So therefore that is a 0. 0 times time is just 0. So 1/2 acceleration times time multiplied by 2 to get rid of the half. And divide by A on both sides, divide by acceleration, so it's going to give us this. And finally square root it so you can have the time isolated. I don't want time squared, I just want time. So square root of 2 times delta x over acceleration on the x-axis is equal to the time it would take. Alright, we have the displacement and we have the acceleration, so we'll plug them in. Let me do that here. Time is 2 multiplied times the displacement of 6 meters or an acceleration of 5 meters per second squared, and the whole thing is square rooted. So the answer for the time would be 12 divided by 5, and square root that answer, 1.55 seconds. So that will be the answer for part B of this problem. It will take 1.55 seconds. I'm going to go ahead and put that here. That was part B of this problem. Next, they're going to go ahead and ask you, suppose that the mass of the puck is doubled. What is the puck's new acceleration down the ramp? And for that one, I want to remind you that when we solved for the formula for acceleration, it was g times sine of whatever angle the hill was. And you'll notice the lack of m. There is no m there. Therefore, the mass is irrelevant here in this problem. Okay, so it's just going to accelerate at the same rate whether you double it or keep it the same. Alright, so the answer is it will make no difference. Alright, example 6. On this problem they say the following. A woman weighs a fish with a spring scale attached to the ceiling of an elevator. While the elevator is at rest, she measures the weight to be 40 newtons. Okay, so there she is in an elevator weighing a fish. Scenario is a little bit strange, sure, but okay, let's not worry about it. So it says it's 40 newtons. That is the weight of the fish. So erase the previous problem. Okay, so that'll be force due to gravity is 40 newtons. While the elevator is at rest, so it's not moving. Okay, so only gravity is acting on it. Then they ask you, part A, what weight does the scale read if the elevator accelerates upwards at 2 meters per second? Alright, so now that's going to be an issue for us. Figure out if we begin accelerating at 2 meters per second, that will change what the elevator says. Okay, now let's go ahead and start. First of all, I want to go ahead and figure out what is the mass of this fish. So I know that force gravity is just mass times gravity. So I want the mass, I'm going to divide both sides by gravity. So therefore the mass of the fish is force gravity over g. So it'll be 40 newtons over 10 meters per second squared. So it is just 4 kilogram. It is a 4 kilogram fish. Alright, so that is our mass. Okay, great. Now, what will be the new force on red on the scale if now we're changing the acceleration? Okay, so we have the mass, so that's going to go right here. It's the acceleration that we got to spend a little bit of time on. Okay, so this is while the elevator force going up. I'm going to label it F up. Alright, and mass is 4 kilograms. Acceleration is 2 things acting on it. It is gravity pulling down plus an elevator going up. So 10 meters per second plus 2 meters per second. Alright, due to the accelerator going up. It's like, but if the elevator's going up, why would we add them? Alright, because it would increase to the gravity. Alright, so that would be a 12. Okay, so that's going to go ahead and be 12 meters per second. And multiply on, so the scale will read 48 newtons. So that will be, and the answer for part A. So it used to read 40, but its accelerator is moving upward very quickly. It's going to go ahead and read 48. Part B, they ask you the scale. What does the scale read if the elevator accelerates downward at 2 meters per second? Okay, so now the elevator is accelerating downwards at 2 meters per second. Okay, at this point, we will use very similar formula. We have the mass of the fish. So now I'm going to put force down. It's going to look like this. 10 meters per second. In this case, minus 2 meters per second. Okay, and so you subtract and then multiply times 4. So that's going to be 4 kilograms. That's going to be an 8 because we're subtracting. Okay, and multiply both of these. 4 times 8 is 32 newtons. So while the elevator is moving down, the scale would read 32 newtons. Alright, part C, if the elevator cable were to break, what does the scale read? Alright, so we're assuming the elevator cable breaks. Now we're free falling. And what would the scale read? By the way, if you're worried for the woman, the elevator does have brakes in case that ever happens. Don't worry, she and the fish will be fine. Okay, so I'll put F for free fall. We're free falling at this point. So how fast are we moving? We're moving at 10 meters per second downwards. Okay, so it would be 4 kilograms. Gravity is 10 meters per second, but we're moving downwards at 10 meters per second. So I'm going to subtract. So 10 minus 10, that's a 0. So 0 times 4, the answer would be a free falling 0 newtons. That's what the scale would read while we're on free fall. It will be weightless at that point. Okay, so that's example for us and the fish. Let's go ahead and move on to example 17. In example 17, they go ahead and they ask you, problem 17. Starting from rest, an elevator accelerates upwards, reaching and maintaining a constant velocity thereafter until it reaches the desired floor. When it begins to slow down, describe the scale readings during this time. Alright, so as the elevator begins to accelerate, so I want us to describe what the scale would read. So I'm going to write down, as the elevator accelerates upwards, the weight of the fish will increase. That'll be part one. Alright, next. The second part says that the elevator now maintains a constant velocity. Okay. As the elevator reaches a constant velocity, the weight would be the same as the elevator at rest, as if it were not moving because it's going at a constant velocity. So it would be the same as if it were at rest. Alright, and lastly, what happens to the weight read on the scale when the elevator begins to slow down? It's still moving upwards, but it's slowing down. What would happen to the weight? In that scenario, the fish would go ahead and there'll be less mass, so it will weigh less, I'm sorry. As the elevator decelerates, well, we normally don't say that. We say it has negative acceleration. Okay, the weight on the fish will decrease. You would see it become lighter as you're about to reach your floor, and now we jump up. If you've ever been in an elevator that is fairly quick, not some of the slow ones, you can't really tell, but if you've been in an express elevator that really pulls you up really quick, when it first takes off, you do feel pretty heavy, and when you're reaching your floor, it's about to slow down, then all of a sudden you feel pretty light. Alright, so let's go ahead and move on to our next problem, and this is problem number 18. Is also the last problem for this section, so let's go ahead and work on it. It says, find the initial acceleration of a rocket if the astronauts on board experience 8 times the normal weight during an initial vertical ascent. Okay, so what will be the acceleration for the astronauts, okay, at this point, if they're experiencing 8 times their weight? Alright, so we have force equals mass times acceleration, and so I want to know what is the acceleration if they're experiencing 8 times their weight. Okay, so therefore the answer would be, well, if they're 8 times more, 8 times f, the mass remains the same, so therefore must be 8 times the acceleration as well. Put parentheses around it instead. Okay, and so that way they're equal to each other. So 8 times their acceleration going upwards. Alright, but what exactly is the acceleration though? The answer to that question, well, let's look at this one. What two components are made from that, the acceleration? It would be 1 from gravity plus 7 from the acceleration of the rocket. Okay, so acceleration of the rocket going up plus 1g from gravity from planet Earth. So the actual answer is the rocket is accelerating at 7, and that's how you get the 8 total acceleration. Alright, so that goes ahead and takes us to the end of this unit. So we covered Newton's third law and some applications of it at an angle and moving objects and an elevator as well. Alright, thank you so much for watching.